Signals and Systems, Common Signals, series on Signals and Systems, lecture number 1.12. In the study of signals and their transforms, in the study of systems and their analysis, we encounter certain signals frequently. For example, step function, impulse function, sample function. These are all appear very often in the study and analysis of signals and systems. They are encountered so often, they are used so much in the analysis, in the study, that they are called, they are labeled as common signals or standard signals. In the present session, the focus is on these standard or common signals. We consider their definition. After that, we also go a little bit deep into their properties so that we can have a better understanding regarding their nature. Before going further, it requires to be mentioned a fact, an observation regarding many of these common signals. They are associated with one or more features which are unreal, which are physically unrealizable. For example, certain signals, for example, unit step function, it changes its level in no time, in a time duration of 0. In practice, in reality, it is not possible. Every change requires certain amount of time, certain duration of time. Similarly, impulse function, it assumes infinite amplitude. In reality, in practice, no signal can have infinite amplitude. Hence, one can say, one can conclude these signals, or most of the signals, they are mathematical and they are not feasible exactly in reality. However, several times, in several situations, real signals can be approximated to these mathematical signals that are going to be introduced, discussed here. With this small brief, let us move further to consider signals one after another. To begin with, we consider impulse function. Impulse function is a variant of pulse function. It is not an ordinary function or ordinary signal. It has certain special significance. To understand more about this function, consider two terms: generalized function, singularity function. What are generalized functions? These are impulse function and its derivatives. Singularity functions are step function, impulse function, and its higher derivatives. As already mentioned, impulse function is not like any other ordinary function. It has certain speciality. Not only speciality, it has certain significance too. Impulse function falls mathematically in the category of singularity functions, generalized functions. Now, let us move to the definition of impulse function. Impulse function is usually indicated by delta. It has two versions, CT version, continuous time version. It has DT version too. Both versions we consider while giving its definition. As already mentioned, impulse is not an ordinary function. The continuous time unit impulse is defined as delta of t is 0 at t not equal to 0, and integral minus infinity to plus infinity delta of t dt equal to 1. Notice the amplitude of the function is defined at all instants of time except t equal to 0. When t is not equal to 0, it is 0, but at t equal to 0, it is not defined. The definition consists of two statements. Now we consider dt version of impulse. It is defined as delta of n is 1 when n is 0 and 0 when n not equal to 0. This is a dt version. One of important properties of dt impulse is sigma n minus infinity to plus infinity f of n delta n minus k equal to f of k. This is similar to sampling property. Now we go a little bit deep into the concept and formation of an impulse function. A unit impulse can be considered as a unit area, zero width pulse. This pulse can be a rectangular, Gaussian, triangular, exponential, or many other forms. This statement requires some explanation. To describe, consider a rectangular pulse. Let us suppose its amplitude is A and duration is tau. Now area of this pulse is A tau. Let us suppose it is normalized to 1. A tau is 1. Now consider reducing tau while maintaining area of the pulse constant, that is equal to 1. As you reduce tau, A keep on increasing, and as tau becomes or tends to 0, then the pulse becomes a spike like this with infinite amplitude. Of course, area remains at 1. This spike, which results when duration of pulse tends to 0 while maintaining area constant at 1, is called unit impulse. Unit refers to area being 1. One can consider a Gaussian pulse instead of rectangular. One can consider triangular. One can consider exponential pulse, or one can consider pulses of several other forms in deriving an impulse function. If Gaussian pulse is considered, then definition of delta of t becomes limit tau tends to 0, 1 by tau e power minus pi t square by tau square. Gaussian pulse is one which we come across frequently in the study of engineering. It's also called bell curve. It appears something like this. If one considers triangular pulse, then the definition of delta of t becomes limit tau tends to 0, 1 by t, 1 minus mod t by tau. This is the definition, mathematical definition of triangular function mod t less than tau. This is the expression. It is 0 when mod t is more than tau. When we consider two-sided exponential pulse, then definition of delta of t becomes limit tau tends to 0, 1 by 2 tau e power minus mod t by tau. When single-sided exponential pulse is considered for the derivation of impulse function, then impulse function becomes limit tau tends to 0, 1 by tau e power minus t by tau u of t. A sample function can also be considered. And then impulse function becomes limit k tends to infinity k by pi sample of kt. Now properties of impulse function, they are considered here. One of the important properties of impulse function is sampling or shifting property. Mathematically, this sampling property, it is described by this integral. Integral minus infinity to plus infinity f of t delta t minus t naught dt becomes f of t naught. So the importance of this property is one can find the value of a function at a particular instant t equal to t naught by computing this integral. Some function is there, let us say, and I want to know the value of this function, amplitude of this function at a particular instant, let us say t equal to t naught. Then by doing this integration, value of the function at t equal to t naught can be determined. When t naught is 0, then the second step, integral minus infinity to plus infinity f of t delta t dt is equal to f of 0. This is a sampling property with t equal to t naught. We consider another important property, replication property. Integral minus infinity to plus infinity f of tau delta t minus tau d tau. It is equal to f of t convolution with the delta of t equal to f of t. The point to be noted here in this replication property expression is when a function convolves with the impulse function, the resultant is the function itself, no change. That's why it is called replication property of impulse function. Some more mathematical identities may be useful in the study and analysis of signals and systems. Delta of minus t equal to delta of t. Delta of at, time scaling, it is equal to 1 by mod a delta of t. T delta prime t equal to minus delta of t. Here prime indicates differentiation with respect to time. F of t delta of t is f of 0 delta of t, and integral minus infinity to plus infinity f of t delta prime of t dt is f of prime of 0. After having some idea regarding impulse function, now we move to another important function or signal. It is step function. It is indicated by u. It also has two versions, CT version, DT version. First we consider CT version. In CT case, unit step is defined as u of t is 1 for t more than or equal to 0. It is 0 for t less than 0. Notice it is characterized by a discontinuity at t equal to 0. In fact, it appears like this. It is 1 for t positive. It is 0 for t less than 0. In dt case, it is defined as u of n is 1 for n more than or equal to 0. It is 0 for n less than 0. And u of minus n is 0 for n more than or equal to 0, and it is 1 for n less than 0. Now, step function and impulse function. These two are related. That relation is described here. In case of CT signals, u of t is integral of delta of t. Step function is integral of impulse function, or impulse function is differential of step function. In case of dt signals, u of n is sigma minus infinity to n delta of k. It is equal to k 0 to infinity delta n minus k. This is step in terms of impulse. Impulse can also be expressed in terms of step as u of n minus 1. Triangle function, it appears like this. Its symbol is tri. Sometimes it is also indicated by triangle symbol or delta symbol. It is defined as tri of t is 1 minus mod t for mod t less than 1 and 0 for t mod t more than or equal to 1. Similarly, one can define a rectangular pulse also. This one is also used frequently in the subject signals and systems. In fact, it is a practical signal. It is called gate function. Another signal, sample function. This is known as filtering or interpolating function. It is defined as sample of t is sin t by t. It is product of an oscillating signal sin t with a period 2 pi and a monotonically decreasing function 1 by t. Thus, sample t exhibits damped oscillations of period 2 pi with amplitude decreasing continuously as 1 by t. It is an even function of its argument t. What he says is, it is product of two functions. One is sin t. Sin t, when sketched, it appears like this. Negative side also it appears like this. 1 by t, when sketched, it appears like this. Like this. Product of these two is sample t. Some properties of sample function. Sample t is 0 when t equal to plus or minus pi, plus or minus 2 pi, plus or minus 3 pi. And the sample 0 is 1. That means sample function is 1 at t equal to 0. Another function also appears in the study, that is sinc function. By definition, sinc t is sin pi t by pi t. One can notice it is sample pi t. Sinc function and sample function, they are related. That relation is given here in this form. Sinc t is sample pi t. Another property, integral minus infinity to plus infinity k by pi sample kt dt. It is 1. Sample function can also be related to impulse. That relation already mentioned, again it is being repeated here. Limit k to infinity k by pi sample kt equal to delta t. Another function we consider an important one is signum function. It is defined as signum t is 1 for positive values of time, minus 1 for negative values of time, and 0 when t equal to 0. It is related to unit step through this relation. Signum t is minus 1 plus 2 u of t. How signum function looks like? This side, positive time side, its amplitude is 1. Negative time side, its amplitude is -1. Just by mere observation with the naked eye, one can find lot of similarity between signum function and step function. That relation is described here as signum t equal to -1 plus 2 ut. Now, some more information regarding signals, regarding their sidedness. A right-sided signal x of t is one for which x of t is 0 for all t less than t naught, where t naught can be positive or negative but finite. It is called positive time signal if x of t is 0 for t less than 0. Sidedness is being described here with respect to continuous time signals. Same thing applies to, same ideas apply to discrete time also. A left-sided signal x of t is one for which x of t is 0 for all t more than t naught, where t naught can be positive, negative, but finite. And it is called negative time signal if x of t is 0 for t more than 0. In other words, a positive time signal can have non-zero values only for t more than or equal to 0, and a negative time signal can have non-zero values only for t less than or equal to 0. If a signal has non-zero values for some t less than 0 and for some t more than 0, then it is called two-sided signal. Now this sidedness is being given, being explained in terms of discrete time signal. A right-hand sequence x of n is one for which x of n is 0 for all n less than n naught, where n naught can be positive, negative, but finite. If it is greater than or equal to 0, then the resulting sequence is called causal or a positive time sequence. A left-hand sequence x of n is 1 for which x of n is 0 for all n more than or equal to n naught, where n naught can be positive or negative but finite. If n naught is less than 0, then the resulting sequence is called anti-causal sequence. A signal that has finite duration on both left and right sides is known as two-sided sequence. These three statements, these 3 points in the present slide, these are discrete time versions of the statements or points given in the previous slide. Before closing, we consider another important point pertaining to signals. A signal cannot be simultaneously band limited and time limited, but a signal can be unlimited simultaneously in both time and frequency domains. What is this band limited and time limited? A signal can be expressed in time domain, it can be expressed in frequency domain. If the time duration of the signal is finite, then we say the signal is time limited. If it is infinite, then it is unlimited in time. Now we consider same signal in frequency domain. If the frequency range of the signal or band width of the signal, if it is limited, we call that signal as band limited. Otherwise, it is unlimited in band. With this small introduction to band limited, time limited, we again go through the statement. A signal cannot be simultaneously band limited and time limited, but a signal can be unlimited simultaneously in both time and frequency domains. As a matter of fact, this statement is being given. Proof is available, but first let us have an idea regarding band limited and time limited natures of signal. Now we come to an end to this session. In this session, we considered certain common signals, standard signals. We considered sidedness of the signals. Hope this session is useful to you. We meet in another session with another topic soon.